we're going to do a prototype of the game of Scrabble. We're going to try and find the best Scrabble word given some tiles that a user has and some provided dictionary. Let's take a look. Of course, we're going to start again with our dictionary, and we'll process this dictionary. So here we know that the processing of this dictionary is fairly straightforward. We have our word list, which is just each word pulled from this thing. We strip off the white space for each one of these lines in this file. In the game of Scrabble, it's also the case that we are not allowed to have proper nouns. So here we might say the way that we're going to remove proper nouns is by looking for each word for the word that we have in our word list. If the 0th letter of this thing is lowercase, and we also might want it to be the case that we remove anything that has punctuation. So we might have something like this. If all of the characters or the Unicode code points, to be stricter in our terminology, if all of these are alphabetical or even a lowercase alphabetical letter, actually, we can even do this for each character in W, because in the game of Scrabble, because you don't have tiles that have things like umlauts on them or cedilla, you can't even have a word that has anything that's not an ASCII lowercase letter. It's only A to Z and then the blank tile, I guess. And so here, this is what our word list might look like. And here we can do this as a sequence of these list comprehensions, or of these set comprehensions rather, or we could change these to be, generator expressions. It really comes down to what we want to do. Let's change this to be a generator comprehension, and then we'll materialize it at the very end. Like that. So here we can print out our word list, and we can see if this looks about right to us. And of course, we have to, there we go. And so I think that looks just about right. Now, if we're going to mock up this game, we'll take this kind of test-ish driven development approach, but a very, very lightweight form of this. And so we can think, if we're playing the game of Scrabble, we have some tiles that we're given. And those tiles look like this. We have a T tile, we have a Z tile, we have a P tile, we have a Y tile, we have an O tile, we have an N tile, we have an H tile, and I guess we're cheating because I think you're only allowed to have 7 tiles, but here we have enough tiles. And I wonder what the best word we can make is. If you can guess what the best word you can make is, write it down now and see if your answer is right. Here, we're going to do something like find Scrabble. And again, we're given some word list, and we're given the tiles that we have. And here, part of what we like to talk about when we talk about things like the most appropriate data type is to build up a correspondence in your mind between what is the nature of the problem I'm trying to solve and what tool do we reach for. There are a lot of questions that people have about things like, well, what's really the difference between this and that? What's the difference between a set and a frozen set? What's in between a list and a tuple? And here we can think, if we have just a nice correspondence in our mind behind each one of the built-in data types and what they really represent, we can say, you know what? A list is any case where we want a collection, where we're going to loop over the elements and do the same thing to each element. A tuple is any case where we have a record, where we want to unpack or destructure the fields. A set is any case where we want to do, this is a collection of unique elements. So we want to do a set operation like a union or something like that, or we want to do some sort of looping, but we don't care that this is machine ordered. And a dictionary is any built-in, or is any structure where we want to maintain some correspondence between some key and some value. And so we want to do a lookup, or we want to do a membership check, or these days you can actually do set operations on the dictionary, or maybe some kind of set operation maybe, or some sort of looping over the correspondence, probably in some sort of insertion order if we're using Python 3.4 later. So here this is a tuple. This doesn't really look like a record. This really looks like a collection of the tiles that I have. So maybe that's the appropriate way that I might do this. Now I will hard code my word list. And so we'll say we have an option of the word Python, or we have an option of the word pot. And presumably there is a scoring mechanism behind this as well. Which of these words do we choose if we're playing Scrabble? Well, we probably want to choose the longer word because we have some sort of scoring mechanism. Anytime you look at some code and you say to yourself, there's another consideration here. but I'm not really sure how to lock that consideration in a fashion where somebody's not going to come back to me later and change it. That is where you reach for some level of abstraction or some advanced feature. In other words, I know that when I call find Scrabble, this find Scrabble should give me an answer, given my tiles and my word list. Well, what should it give me, pot or should it give me Python? Well, if I think about it, there are rules behind this. Like, obviously, the longer word is probably better than the shorter word. But there's also rules behind it. What's the value of the individual tile? What are the Scrabble scores? There's also another rule. If you use all of your tiles, maybe you get some extra points. There's also another rule. If you think about laying this out on the board, if there's a double letter score, a double word score. And so there may be many different considerations that judge which of these is better. In that case, one of the ways that I can rapidly iterate without coding myself into a corner where I have to change something later is making use of tools like generators. Generators are not just program structuring tools, they're also rapid iteration, rapid development tools, because they give you the ability to encode something, but to then swap it out later without disrupting the code that you already wrote. And so again, here, I might actually yield the answers and then adjudicate the answers separately. So here, I might do something like this. The best answer is the maximization of the answers over some particular predicate. And here, this is a particular predicate making use of some, score mechanism that I can encode here. And here, we'll make this based off of just the length of the word. And since that's the case, I might want to materialize this ahead of time just so I can, eyeball both of these pieces. But what you can think is I can start with something very simple, and I can leave this code intact once I've locked it in, and then swap this code out for a much more sophisticated predicate that maybe not only takes into account the word, but maybe the state of the board. So here, let's take a look what our best answer is, and let's take a look at what all of our answers are. Because we materialized it, it's sometimes good to just double check, because from the answer to the best answer is something that we might also want to eyeball. We might also want to spot check. So here we go. Now, obviously, this doesn't return anything, so we'll have to make this kind of work. So here for word and word list, we'll just yield the first word, and we will break after this. And we have a simple word list. And you can see here, maybe just for consistency with what we had before, we can make this a set of words. So it says the best answer is pot. Why? Well, because it's not really giving us all the possible answers, it's just giving us the first one that it saw. So we can remove this break and we can see, okay, yeah, it's just using the length of the word here. Now, what we know is we need to do another sort of criteria to check this. We need to not yield every possible word. We need to yield every possible word subject to some criteria, namely that it is possible to make out of the tiles. And this is the case where something like our collections.counter can be very helpful because the collections.counter can be compared to another counter. So we might do this. Pre-compute the counter for the tiles and check to see if the counter for the tiles is greater than or equal to the counter for each one of the individual words. And here you can see we get all of our answers. Now let's actually pull in our real word list and see if this works nicely for our real word list. So let's pull in our real word list and the code that we wrote and see if these two pieces work together to solve the problem in the way that we anticipate. So we'll do this. Let's grab our code from above for the real word list. So let's make sure that we can grab that one more time. And we'll see where this takes us. So that's our real word list code. That's our whatever. We won't use this hard-coded one. And we'll see here is the counter. Okay, and we won't print out the word list because that's a little bit of noise. And so you can see there's quite a few choices that we have. Phony, Tony, though, typo, top, nth, and there we go. Now that we know that at least part of this works, we might say, well, you know what? We actually want to improve the quality of this predicate. We want to include some sort of scoring. And so here we might have tile scores as another parameter. But notice it doesn't require that we change this algorithm at all until we're ready to time that and maybe optimize that separately. So we might say, okay, tile scores, and I kind of know what the tile scores are for Scrabble. I know, for example, the P is worth maybe 1 point, the H is worth 1 point, the O is worth maybe 1 point. I know a Q is worth a lot of points, or maybe a Y, make the Y worth a lot of points. And let's actually let's make the Z worth a bunch of points. Make that worth like 100 points. So here we might say it is the sum of the tile scores, getting each character for the character in the word, returning that, and we might say, we might even have a bonus equals, I think you might get double the points. So you might say 2 if the word, the length of the word is equal to, I think, 7, or you could maybe even say, bonus length equals 7 to parameterize that. That's a small detail, otherwise 1. And this is multiplying times our bonus multiplier. So you can see here, there we go. And of course, we need to, make this a default of 0. And so here you can see Oz is worth way more than Python based off of this criteria. And you can see we've actually been able to nicely iterate to a more advanced version of this game, which can now accommodate some additional rules that might be house rules of ours without really having to revisit this code. So part of that live coding and iteration process is about seeing past just getting some code working to figuring out how to segment that code so that you can not only get code working, but you also don't have a lot of churn there. Because part of the lie of live coding is, yeah, it looks so smooth if you already know what the answer is, but in reality, actually writing out this code in a deliberate process does involve a lot of churn unless you have a methodical direction that you want to take.